this chapter, we're going to start looking at applications of derivatives. This lesson is a continuation of our look at related rates.
All right, everybody, let's take a look at some more related rates problems. Sawdust is blown into a conical pile such that its radius is always half the height. Okay, well, right away, if I'm going to put some information in what I know, here's my conical pile of sawdust. Okay, I know that the height here and the radius here, based on what I've been told there, I know that my radius is always half the height. Okay, well that's an important first bit of information there, a nice relationship between those two variables. Okay, because as soon as I saw that conical pile of sand, I suspect we're going to be talking about volume. And volume, the formula for the volume of a cone, has radius and height in it. Now, if the sawdust adds 3 pi cubic feet to the pile per minute, okay, well there we go. So I know dV by dt is going to be 3 pi cubic feet per minute. So I know a rate, dV by dt. And the question is, how fast is the height of the pile changing 15 minutes after it starts? Okay, so we are looking for dH by dt. Don't know what that is, but I know that that's what I'm looking for. Okay, and I know one more thing. I know we're looking for how that is increasing at the 15-minute mark. Okay, now that's interesting because in a lot of cases when we give a question like this, we're actually giving the height. Well, we don't often give the time here. So we're going to have to wait and see how that plays into it. But because I'm looking for dH by dt and I've got dV by dt, I need a relationship between V and H. Now I know that the volume, the volume of a cone is going to be 1/3 pi r squared height. Okay. So I've got the two variables in here, and you can visualize this as the sawdust is being blown on this and the pile is growing. Not only is the height changing, but also the radius of the base there is changing. So both of these are variables. So I wouldn't want to plug in anything too soon here. However, I can rewrite radius in terms of the height variable. So it's not like I'm changing r into a constant. I'm replacing it with another variable. And so I can rewrite this as 1/3 pi h over 2 squared multiplied by h. And so now my volume will be 1/3 pi, this will be h squared over 4 multiplied by h. And then I can put that all together and we'll get pi multiplied by h cubed over 12. So there's my relationship between volume and my height. Good. Now I can take the derivative because now I can pull out of this kind of static relationship. I can pull out this dynamic one where I've got my volume changing and my height changing. So dV by dt. Now remember, time is the independent variable here, even though time does not show up. So I'm going to have to take the derivative implicitly. Okay, I know that h is a function of time. I just don't know how. So I'm going to bring down that 3, so 3 pi h squared, this is all over 12, and then I got to multiply by the derivative of that h function, whatever relationship that is. And I don't know what that is quite yet. But that's okay, because I'm looking for dH by dt. Now, I know that dV by dt is 3 pi. Okay, over here, I can simplify this a little bit, because I got 3 over, actually, I'm going to leave that 3 pi in there because I'm going to be able to cancel those out right away. This is over 12. Okay. Here's my problem. I am looking for dH by dt. That is I'm okay with that being unknown because that's what I'm looking for. I am not, however, okay with h being unknown. Because if h is unknown, then I really can't figure out what dH by dt is. So I got to figure out, well, how am I going to do that? And that's okay. That's what the 15 minutes was about. So let's explore this a little bit more here. Because I know I've got a relationship between volume and height, okay? So I know this already. I know volume is going to equal pi h cubed over 12. Figured that out over here. So if I knew what the volume was, I could figure out what that height is that I need here. Well, okay, I'm putting 3 pi cubic feet per minute onto this pile, and I'm waiting 15 minutes, okay? Now, putting that together, that means 15 times 3 pi. That means I've got 45 pi feet cubed on this pile at that moment. So that's going to be pi h cubed over 12. All right, well, wonderful. Well, now I'm going to multiply 45 by 12. I'm going to cancel the pi's, I should say. Probably deal with that right away. Multiply through by 12, and I'm going to get 45 multiplied by 12 is equal to h cubed. Now, the reason I didn't multiply that out right away is because I'm going to try to simplify this as soon as I can. Okay? And I'm just going to do a little... Oftentimes, if I know I'm going to have to simplify it in just a moment here, oftentimes it's less useful to multiply that out. It's more useful to actually factor this. Because I know that 45 is 3 squared multiplied by 5, and 12 is 3 multiplied by 2 squared. Well, notice that I've got 3 cubed in there. I've got 3 factors of 3. So when I take the cube root, okay, when I take the cube root of all of this, that's 3 cubed multiplied by 2 squared multiplied by 5. That's going to be h here. Well, I can take out a 3. And I'm left with the cube root of, that's going to be 4 times 5 or 20. So there we go. Now, I'm going to take this, plug this up into here. So this will be 3 times the cube root of 20. Okay, now my 3 pi's are going to cancel. I will bring up the 12. And I'm going to divide by 3 cube root of 20. Oops, that whole thing is being squared. I put that parentheses in the wrong spot there. I got a little too quick with the parenthesis there. So this is 3 cube root of 20 squared, and this is going to equal dh by dt. Now, I suspect that I would be smarter to just use the calculator here and get a decimal, but let's just simplify this right now, just because it's kind of fun, actually. So this is going to be 12 over 3 squared is going to be 9, and this will be multiplied by the cube root. And now once again, I'm going to break that into its 2 factors. It's going to be 2 squared times 5. So this is going to be 2 to the 4th times 5 squared. This is my dh by dt. I'm probably spending way too much time on this, but whatever. I kind of enjoy playing with the math this way. So 12 over, I've got 4 2's there, so I can pull out a 2, so it's going to be 18 cube root, I'm going to leave a 2 in there, 5 squared is 25, this is going to be the cube root of 50, equals dh by dt. And then between these two right here, there's a common factor of 6. So it's going to be 2 over 3 multiplied by the cube root of 50. I don't think I can do anything more to make that any prettier. However, depending on who your teacher is, you might need to simplify that a little bit further. So I'm just going to go to my calculator and enter in 2 divided by 3 times the cube root of 50. And it looks like I'm getting 0.18. What have we got here? The units would be feet per minute. And there's my dH by dt. Okay, this is an exact form. This is in a decimal form. Yeah, that's maybe still a little bit messy. That looks a little bit better. All right, this is a different sort of a problem than the ones that we've been doing up to this point here. Little girl flies her kite directly over a tree located 70 meters east of her. Now, if you just visualize that, we've kind of described a triangle immediately. So let's take a look at what we know here. Well, so here's our 70 meters away. So we've got this girl right here. Okay, and I'm just going to use dots for this. And then she's got her kite up here, directly above this tree. Now, don't worry about the tree here. I'm not even so sure why I think it's just so that we could have this get a better sense of the distance here, the 70 meters. Now, the wind stops suddenly, and the kite starts to drop vertically at 1.5 meters per second. Okay, so let's call this y. we'll call this distance here x, and we'll call this z there. I mean, why not? X, Y, Z. A, B, C if you really want here. Now, it starts to drop vertically. I'm given a rate here, 1.5 meters per second. Now, that means dy by dt, that is the rate of change of the y variable. It's 1.5 meters per second. But not only that, because the y variable here is getting smaller, it's negative. That rate of change is negative. So now the question is, how fast will she have to reel in the kite string to keep it taut when it is 14 meters above the ground? Okay, so how fast will she have to reel in the kite string? Okay, now that's a rate. And remember, this is the string. So what I'm asking for is dz by dt. I don't know what that is, but I'm looking for dz by dt. And I'm looking for it at the moment when it is 14 meters above the ground. Okay, that's the y variable. So 14 meters. Okay, good. So I've got y and I've got z, okay, or dy by dt, dz by dt. I've got two rates of change here. I need to get an equation relating those from this triangle, and I hope it's pretty clear that what we're looking at here is the Pythagorean Theorem. Okay, x squared plus y squared is going to equal z squared. Okay, great. Now, in the last lesson that we looked through, okay, I made a point about not substituting in variable or values in for variables. Now, y is a variable. Okay, y is dropping. Okay, the wind stops, the kite falls here. Y is changing in time. So I am not going to plug in that 14 right away. But there is something else going on here though. X, although it's a variable in my equation, x never changes in this scenario. Horizontally, the kite is always directly above that tree 70 meters away. That's the scenario that they're trying to describe here. So actually, I can substitute that in right away. And this is the first time we've had a question where we can actually do that. And I hope you get a sense of what the scenario is describing and why that is okay to plug that in. That will not change in this scenario. Now, y is going to change and z is going to change, so I need those to stay in there so that I can take the derivative and get their change, the dy by dt to the dz by dt. So now I've got an equation that is just in terms of y and z. So now I'm going to take the derivative. The derivative of 70 squared is 0. That's why I didn't even bother to square that. It's just going to go away. The derivative of y squared will be 2y. And remember, the independent variable is time. So I've got to take the derivative implicitly. So dy by dt. This will equal 2z dz by dt. Okay? I am looking for dz by dt. So I'm going to divide both sides by that 2z. Now, the nice thing is the 2's cancel. So we're left with y over z dy by dt is going to equal dz by dt. Wonderful. We've got a beautiful little relationship here. Okay. Now, I know that at the instant that I'm interested in here, I know that y is equal to 14. I know that dy by dt is negative 1.5, and I could have written that as a fraction, negative 3 over 2. This is going to be equal to my dz by dt. What I don't know is the actual value of z at that moment. But I do have the relationship between those two. Okay, so now I'm going to come down here, and although I didn't need to square the 70 before taking the derivative, I'm going to have to do that now because to fill in the equation, I need that bit of information. So 70 squared is going to be 4,900 plus, okay, well, I'm going to write that in there. 14 squared is going to equal z squared. Okay, so 14 squared is going to be 196. So 4,900 plus 196 is equal to z squared. 4,000... sorry, that is going to end up being, I just want to make sure that I'm doing this correctly here because I have screwed up little bits of this sort of addition before. So just looking at my calculator here. So 5,096 is equal to z squared. Okay, now I'm going to take the square root of that. to get z. Now that could be plus or minus, whoops, plus or minus. However, we all know in this context that it's not negative. It's just going to be the positive square root of 5,096. Now, I'm leaving it like this because the question gave me a value to the nearest tenth. I'm actually going to give the answer to the nearest tenth. So I'm going to plug in this square root of 5,096 right here. So now what I'm going to do is I'm just going to evaluate this in my calculator. So 14 times negative 1.5, and then I'm going to divide that by the square root of 5,096. And we get here a value of negative, now it's going to round to negative 0.3. What have we got here? Meters per, I think she's pulling it in per second. Yeah. dz by dt. So at that moment that the kite is 14 meters above the ground, she needs to be pulling that in, okay? But basically close to like 30% of that, 30% of a meter here, about 30 centimeters a second here, okay? To get that to stay taut. Interesting question, okay? This is a really good one. Okay, this is a really good one to pay attention to because of that constant that pops up early on in this problem. All right, this question is another kind of a classic in the area of related rates. Okay, small plane leaves an airport at noon, traveling 120 kilometers per hour. So right here, there's a rate. Okay, on a bearing of 345 degrees, and then at 1:30, a second plane leaves the same airport, traveling at again another rate, 160 kilometers per hour. Again, we're given a bearing 75 degrees there. Now, the reason I haven't popped this out and dropped this into a no section yet with these rates here is because I'm going to need to draw this thing a little bit before I start to identify what those rates are. So here is what I know. Okay, I know that we've got our compass. So here's north. And the small plane leaves an airport at noon. Okay, well that's important. Traveling 120 kilometers an hour on a bearing of 345. Now, a bearing of 345 means that's going to wrap all the way around. That's actually going to look like this. Okay, where this is your 345 degrees. And right there, this is the vector that first plane is going on. So let's just call this distance here A. Okay, and so we know that dA by dt is going to be 120 kilometers per hour. Now at 1:30, a second plane leaves the airport traveling 160 kilometers an hour on a bearing of 75 degrees. Well, a bearing of 75 degrees is going to look like this. Okay, let's call this B. And we know that dB, I want to make sure you can see that, dB by dt is going to be equal to 160 kilometers per hour. Now notice both of these are positive because those vectors are getting larger. Okay, the values are getting larger. Now the question is, how fast is the distance between the planes changing at 3 p.m.? Okay, so we are looking for, we'll draw a line right there, C. Now, this right here is 75 degrees. The angle from north all the way around is 345. It shouldn't take you too long to realize that this right here is 15 degrees, which means that we're actually looking at a right angle triangle. Okay, so the relationship that we're going to explore here is going to be a squared plus b squared equals c squared, okay? So we can write that over here. A squared plus b squared is equal to c squared. Now, I am looking for the rate at which the distance between them is changing. So I am looking for dc by dt. I know that's the thing that I'm interested in. Okay, well, this is interesting because not often do we run into problems where we've actually got three different variables in the problem, and we've actually got derivatives for two of them, and we're looking for the derivative for the third. So we should be able to jump right in here. So taking the derivative, I'm going to get, remember the independent variable is time once again, and I know I've said that a lot, but I'm going to keep saying that so that you believe me. Okay, we're going to take the derivative here. That'll be 2a dA by dt plus 2b dB by dt is equal to 2c dc by dt. Great. I am looking for dc by dt. That's the unknown here. So I'm going to divide everything here by 2c. Now, notice that I can factor out a 2 from these two expressions, so those will cancel with that 2 right there. And so on this left-hand side, we're going to get a dA by dt plus b dB by dt all over c is going to equal dc by dt. Okay, well, I know dA by dt, I know dB by dt, yeah, but I don't know a, b, and c right now. But I was given one more little bit of information here. The question told me that I'm interested in how fast this is changing at 3 p.m. Okay, that means that first plane, which started at noon, traveled 120 kilometers an hour for 3 hours. That means A has gone 3 times 120, okay? It's gone 360 kilometers. Well, I can do a similar sort of calculation with B, okay? B went, the B plane was going, let's go back up to here, look at it, 160 kilometers an hour. It left at 130, which means it had only been traveling for an hour and a half. Okay, when you multiply 160 by 1.5, you're going to get 240 kilometers. Okay, so now we're going to take this and we're going to use the Pythagorean Theorem to figure out what C is. Okay, because we know that a squared plus b squared is equal to c squared. So this will be 360 whoops, wow. That was so automatic. I wanted to put a degree symbol there. That's crazy. 360 squared plus 240 squared is going to equal c squared. I'm just going to do this on my calculator here. I'm not entirely sure if this works out to be a nice number or not. Okay, 360 squared plus 240 squared, that is a big number. And it doesn't work out. It doesn't work out super nicely here. Okay, it probably can be simplified here, but I'm very likely going to convert that. This is going to end up being C is going to end up being the square root of 187,200. Which, I mean, at the very least, I could pull out a 10 out of that, but based on the numbers here and what we're looking at here, I probably will I'll just plug those in and get the decimal value here. So I know now that A is going to be 360 and that is going to be multiplied by 120. B will be 240 and I'm going to multiply that by its rate of change, which will be 160. This is all going to be over the square root of 187,200. And this is going to equal my dc by dt, the rate of change of the distance between them. So now, this is all just going to be calculator work. So just go to my calculator over on the side here. 360 times 120 plus 240 times 160. Now I know you can't see this, but I'm really not doing anything all that interesting. 187, 200. And we get 188.60 kilometers per hour, which is approximately equal to dc by dt. And so we probably simply just state that it was like 189 kilometers per hour. Probably just round that to the nearest whole. And there you go. All right. For this question right here, this is another classic related rates problem. In fact, if you go through Take University calculus, you'll probably wonder if any mathematician can properly set up a ladder against a wall here, because they always seem to be slipping down the wall. A 9-meter ladder rests against a vertical wall. The bottom of the ladder begins to slip away from the wall at a rate of 20 centimeters per second. Find the rate at which the top of the ladder moves down the vertical wall when it is, and then we get some scenarios here. So let's take a look at what we know here. And the best thing to do here is actually to draw this out. Okay, so here's our ladder, here's our wall, and there's a right angle there. A 9-meter ladder rests against the vertical wall. Okay, so 9 meters. Now let's call this distance here x. We'll call the vertical distance up the wall y, and we'll call the length of the ladder z, even though we already know at this point in time that that's 9. So here's another example of a situation where this particular variable is actually going to be a constant throughout this scenario. Now, it didn't have to be. Okay, we could easily kind of change this situation a little bit where the length of the ladder changes, but right now there's no reason to suspect that that's the case here. Now, it says the bottom of the ladder begins to slip away from the wall at a rate of 20 centimeters per second. So this is going out, okay, and x is getting larger at 20 centimeters per second. Now, I have to be really careful about this because this is given to me in meters. I do not want to make dx by dt 20. Well, I don't want to interpret that or replace or substitute later on in this equation here dx by dt with 20 because that would imply 20 meters per second. So I need to make this 0.2 meters per second. Okay? Now this is in meters, and I'm good with that. I am interested in how fast dy by dt is changing, so I know that I'm looking for that's my unknown here. And then I've got a couple situations here. Find the rate at which the top ladder moves down the vertical when it is, okay. So first of all, in our first scenario here, we know that y is going to equal 8. And in our second scenario here, y is going to equal 3. Okay, so there's our information here. Now, it should be pretty clear that once again we are looking at the Pythagorean theorem. So x squared plus y squared is equal to z squared. And as in a previous problem here, one of those isn't actually a variable, it's a constant. In this case, it's the z. So this is going to be x squared plus y squared is equal to 9 squared, or 81. Okay, so now I've got a relationship between x and y, so now I can take the derivative to get their rates of change. So remembering that time is the independent variable here, this becomes 2x dx by dt plus 2y dy by dt is equal to 0. Okay, the derivative of that constant will be 0, and it's important that you remember that. Makes a big deal here. Now, because the right-hand side is 0, though, I can get a little lazier. I can divide everything through by 2. That simplifies this down a little bit. Okay. In fact, you're going to notice that in like most cases when we're using the Pythagorean theorem, that 2 is going to be gone. We can get rid of it. So now we're looking for dy by dt. So I'm going to bring this x dx term over, so which will make that negative. It's negative x dx by dt. Then I'm going to divide by y. So dy by dt is going to equal negative x over y dx by dt. Now, it's at this point right here that I'm going to use the information that I was given initially in the problem. So both of my problems here are going to require this particular little expression here. So now I'm going to take a look at, maybe we'll do them side by side. So here's question A, and then we'll do question B over here. Now, I need, though, x and y in order to finish this expression here. Now, I got to take a look at the information that I've got here. I know that y is equal to 8. So in this first scenario here, this is 8, this is 9, and now I'm looking for x here. So this is going to be the Pythagorean theorem. It'll be, we'll make sure it's visible, 8 squared plus x squared is equal to 9 squared. So 64 plus x squared is equal to 81. Whoops, sorry. I just want to make sure that I'm not going to inadvertently grab the wrong number there. So 81 minus 64 is going to be 17. Whoops. Which means x will be the, now this will be the positive negative root of 17. And although I know that we're going to ignore the negative one here because it doesn't make sense in the context of the question. I'm probably like a lot of your teachers where I would just like to see you acknowledge that first. Okay, I really want my students, when they've got the x squared equals 17, to acknowledge that the answer to this problem is the plus or the minus, but I don't worry about the negative one here because it just doesn't make any sense in context. So now my dy by dt, I can come back up here and plug in what I know. This is going to be negative, okay, x is going to be root 17, y we know is 8, and dx by dt was 0.2. Okay, I'm okay with the root 17 in there actually for right now. And if I take 0.2 and divide that by 8, okay, I'm actually going to get root 17 over 40. And I'm okay with how that looks here. This is going to be meters per second. Now I can convert that though into a decimal, which would make that a little bit easier, maybe to get our heads wrapped around what's going on there. So root 17 over 40, that is going to be essentially negative 0.10 meters per second, or 10 centimeters per second, that the top is falling down. Now notice that all on its own, in the math here, a negative pops up. This dy by dt is negative. Well, that makes perfect sense, because if the bottom of the ladder is sliding out, that means the top of the ladder is going to be dropping down. That value is going to be getting smaller. Its rate of change should be negative. That's perfect. Kind of just did it for me. Now, the next scenario that we need to look at here is what happens when y is equal to 3. So here's 3, here's 9, and here's x. So 3 squared plus x squared is going to equal 9 squared. So 9 plus x squared is equal to 81. And if I subtract, x squared is going to equal 72. And in this case here, this is actually a lot easier to work with. This is going to be plus or minus the square root of 72. I know, okay, that I'm only going to use the positive, but I also know that the square root of 72 can be simplified to 6 root 2. Okay? So, now I can take that and go back up to my derivative up here, this dy by dx. Oh, sorry, dy by dt. Whoa, dy by dt. Yeah, I've tried to go through and make it clear that t is the independent variable, and then there I go. Put an x there. So this will be negative 6 root 2 over, and the y value we just learned was 3. And then this is going to be 0.2. Okay, and so now what we've got here is, that's going to be, what do we got here? Well, we can cancel the 3 out, so it becomes negative 2 root 2. And that's going to be negative 2 root 2 over 5. Okay, because of that 0.2. 0.2 is the same as 1 over 5 here. And so there we go. Meters per second. Now, let's just see what that is as a value. Right, so this is going to be negative, or approximately, negative 0.57 meters per second. So notice it's going quite a bit faster at this point right here. And actually, doesn't that make sense? Okay, when the ladder slides out here, okay, it does make sense. Even if the bottom goes out at a constant rate, okay, at a constant rate, the change up here is going to be slight until it's at about a 45-degree angle, and then even though this goes out at a constant rate, the height here is going to drop faster and faster. So good. Makes perfect sense. It's consistent with kind of our experience of what a falling ladder would look like. All right. For this question here, we read that an escaped prisoner is directly beneath the spotlight 10 meters above the ground. If he runs away at 5 meters per second, okay, and so there's my rate of change. How fast is the tip of his shadow moving? Okay, so that's another, how fast, so we're looking for another rate of change. When he is 8 meters from his starting position. Okay, now, okay, directly beneath the spotlight. Okay, there we go. So let's just take a look at what this scenario is supposed to look like. So we've got the spotlight right here, and it is 10 meters above ground. And then we've got this guy running away. Okay, and so he's 2 meters. Now, obviously, my scale is way out of whack, but that's okay. Doesn't matter. The diagram's there just to give us a sense of the relationship between the variables here. Okay, so he's running away at 5 meters per second. Okay, that really has got to be this distance right here. Let's call this distance here x. The reason I do that is if this is our guy running away, then when you measure speed, it's always going to be with reference to a fixed point. So in this case, our fixed point makes sense that it would be the point directly underneath the spotlight. So we know that dx by dt is going to be, what did I read, 5 meters per second. Okay, so that's how fast he's running away here. Now, there are a couple other variables that kind of present themselves here real quick. Notice that, whoops, sorry. Whoa. Notice that this part right here, this is his shadow. So now y is going to be the length of his shadow. But at the same time, the question is asking how fast is the tip of his shadow moving when he's 8 meters from the starting position. Now I'm not asking you for y. I'm not asking you for dy by dt. dy by dt, okay, if we put this up here, dy by dt is the rate at which his shadow grows. Now, yeah, that's part of the problem that we're looking at, but I'm interested in how fast the tip here of this triangle is moving along the ground here. I'm not asking how fast his shadow is growing. Now, they are going to be related to each other, but if the problem is if this guy's running, this point is also moving. So granted, his shadow's getting longer, but he's moving. So the tip, okay, the rate at which the tip moves is going to be affected by how fast he's moving and how fast his shadow is growing. It's a cumulative effect. So really, to determine how fast the tip is moving, I want z. I want to know dz by dt. I'm going to measure that from a position that's not moving, right? And that's that spot right underneath the spotlight here. Now, I could very easily have asked for how fast is his shadow growing, okay? But remember, if I ask for how fast the tip of the shadow is moving, I want to know how fast his shadow is moving, and then in addition to that, how fast his shadow is growing. Those two together, the movement, okay? So it's like this. My fingers here represent his shadow here. It's moving and growing. So the tip is going to be affected by the movement and also by the growth. Okay, so right now I'm looking for a relationship between x and z. Now I also know that we are looking for it at the specific moment that x is equal to 8 meters. Okay, now in this case right here I might be tempted to pull out the Pythagorean Theorem, but notice that I've given no information at all about the hypotenuse. I'm not even asked about the hypotenuse. The hypotenuse is like a non-issue here. So it really has nothing to do with it. In this situation right here, actually what we want to do is we want to build similar triangles. Okay, so 10 to z is going to be similar to, or that ratio there is going to be the same as 2 to y. Okay? I'm going to use similar triangles. Large triangle here is similar to the small triangle. Height to base, height to base. And that's beautiful, except for the fact that I don't really care about y. What I've got is dx by dt. I want the z in there, totally want the z, because I want to grab that dz by dt. But I want x in there. Turns out though that's easily done because y, notice that my variable y here is actually going to be z minus x. Okay, that distance right there is going to be the total distance minus this distance right here. So I can go back up to this ratio up here and go 10 over z is going to equal 2 over z minus x. And now the only variables in there are my z, my x. So now I'm going to cross multiply, if you will. 10z minus 10x is equal to 2z. Let's bring that x term over, bring the z term over, so that'll be 8z is equal to 10x. Okay, and now I'm kind of lazy, so I'm going to reduce this as much as I can. There's a common factor of 2 there, so 4z will equal 5x. And now I'll take the derivative. So each of these are going to be functions of time. So dz by dt, this will equal 5 dx by dt. Remember that the unknown I'm looking for is dz by dt. So dz by dt will equal 5 over 4 dx by dt. Okay, I know that dx by dt is 5, so I can substitute that in. Now, what's interesting about this problem is that notice that I was given a value for x, how far away it is. Okay, how far away the convict is from the right below that spotlight. But in my derivative, it didn't even show up. X on its own as a variable wasn't even part of this expression. That distance right there, that is a red herring. In this particular problem here, that has nothing to do with it. Okay? That is a tempting little morsel that we throw out there because when you start a related rates problem, and if you think back to all the related rates problems that we've done up to this point, there's been this extra little bit of information so that you could fill in the variable here. Well, here's an extra bit of information, but there's no variable to put it in. So that's irrelevant. And so we're going to get, what is this, 25 over 4. And before I write down the answer here, so that's 25 over 4 meters per second, or 6.25 meters per second. That's how fast the tip of the shadow is moving. And again, remember, that is a combination of the effect of the shadow moving because the guy's running and his shadow growing, both of those together. Good problem for a couple of reasons, okay? Using that similar triangles here and that little red herring right there, that 8 meters, that really has nothing to do with the problem at all.